Today we're going to look at one of the applications of the derivative of a function, the idea of local linearization or of a linear approximation to my function near a point. Let's first recall some of the definitions that we'll be using in this lesson. So first, if we're given a function f and a point x equals a, the derivative of the function at that point is given by f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. And remember, this f prime of a gives us the slope of the tangent line. So using the point a comma f of a, and then the slope again is f prime of a, if we plug those into the point slope form of the line, we get the equation y minus f of a equals f prime of a times the quantity x minus a. So this gives us the equation of our tangent line to the graph of f at the point x equals a. Now all I'm going to do is rewrite this equation by solving for y. And then I'm going to rename the function L of x, just standing for the tangent line here. So we get that L of x equals f of a plus f prime of a times the quantity x minus a. This function L of x is what's called the linear approximation of the function f at the point x equals a. So this function L of x gives us a good local approximation for my function f. So when we're close to x equals a, L of x and f of x have y values that are close to each other. And then while f of x might be a complicated function, L of x is a linear function, which is much easier to work with. So let's look at a graph of this to see what's going on. So here's the graph of y equals x squared and its tangent line at the point x equals a. And I'll leave a link in the video description down below for the Desmos graph where I got this, where you can interact with it some more. So the first thing I want to point out is when we zoom in right around x equals a, where we took the tangent line at, we get that the tangent line and the graph are really close to each other, almost indistinguishable between the black curve of the function y equals x squared and the red line of the tangent line. And again, this just illustrates the idea of how close an approximation the tangent line is to the graph around the point x equals a. So we can use the tangent line as an approximation of function values. So for example, if I wanted to approximate the value 1.3 squared, which is the same thing as trying to find the value f of 1.3. Instead of doing that, I can approximate it by plugging in 1.3 into my tangent line equation, L of 1.3. And then we can see on the graph how close these two values are, why this is a good approximation. So f of 1.3 is right here versus L of 1.3, which is right here. So the y values aren't very far apart. And if you actually did the calculations, f of 1.3 ends up being 1.69, while L of 1.3 is 1.6. So again, we can see that the tangent line gives us a good approximation for function values near the point x equals 1. Now if we tried to do this for points that were farther away from x equals 1, my error would be greater because the tangent line and the curve of y equals x squared get further apart as I get farther away from x equals 1. So this really only works for points near where I'm taking the tangent line at. Let's work through an example. So say I want to approximate the square root of 5. I know that the square root of 4 is 2, so the square root of 5 has to be slightly bigger than that, but maybe I want to be a little bit more exact. So we're going to use the idea of local linearization to do this. So first we need to pick our function and a point to find the tangent line at. So the way that you're going to do this is really just replace the number here with an x. So the function I'm going to be working with is f of x equals the square root of x. And then to find the point, we want something that's close to 5, but something that we know f of that value. So 4 seems an obvious choice here because that's close to 5, and we already know that f of 4 would just be the square root of 4, which is 2. Now to find the slope of the tangent line, I need to find the derivative at the point f of 4. So you can use the definition of the derivative to find this. I'm not going to go through that here, but the derivative f prime of x is 1 over 2 times the square root of x. So f prime of 4 would just be 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4. Now we just use those values to plug into my function L of x. So we end up with f of 4, which is 2, plus f prime of 4, which is 1/4, times the quantity x minus 4. So this is the tangent line, the equation of the tangent line at the point x equals 4. So now the square root of 5, which is what we're trying to approximate here, is approximately the same as L of 5, because that would be plugging in the function, or the value x equals 5 into the tangent line instead of into the actual function, the square root of x. And when we do that, we get 2 plus 1/4 times 5 minus 4, which is just 1. 1/4 times 1 is 1. So we get 2 and 1/4, or 2.25. So the square root of 5 is approximately 2.25. If you plug this into your calculator, the square root of 5 comes out to be about 2.236. So we're pretty close by using the tangent line rather than plugging in the value of x equals 5 into the actual function. But using the tangent line still gives us a good approximation, and it's much simpler calculations. So that's how you can use the tangent line as an approximation for your function f of x.